Hello, everyone, and welcome to this week's Crunch seminar. Our first speaker is Dr. Ali Kashefi. He is affiliated to the Department of Civil and Environmental Engineering from the Stanford University. His research interests are computational physics, artificial neural network, and mechanical engineering. Today, he would present to us on the topic titled Physics-Informed PointNet, a deep learning solver for steady-state incompressible flows and thermal fluids on multiple sets of irregular geometries. So without any further delay, let's welcome him for the presentation. You may want to share your screen.
Yeah, thanks for the introduction. Actually, this is my last year of my PhD, so I'm not a doctor officially yet, but thank you for the nice introduction. Today I'm talking about our recent manuscript, which you can find on archive, Physics-Informed PointNet, which is generally a framework for solving partial differential equation on multiple set of irregular geometry, but here we specifically focus on incompressible flows. To give you a sense that how the story starts, I am starting with some motivation and introduction. So imagine that we would like to design a rear wing for this Formula One car. The question is that what is the best or optimized shape for the wing? Or imagine if you would like to design a wing for airplane. So we would like to maximize the lift to drag coefficient, also the lift coefficient. We need to do a bunch of simulations. So each dot shows a simulation using some CFD solver to see what is the best and optimized shape. So at a very high level, we could say that this is a loop. So we need to define some geometric parameters. And then for that specific set of geometry, we use a numerical solver, CFD solver, to find the solution. And then we analyze the results. And then based on that, we adjust the geometric parameters and then repeat the loop. So the most time-consuming component of this process is the CFD solver. And the idea is that we can replace this solver with a neural network to accelerate this process. But when we talk about deep learning, so we at a very high level, we can say that we have two approaches: supervised learning and unsupervised or weakly supervised learning. So when we have a plentiful label data, probably we can use supervised learning. In unsupervised or weakly supervised fashion, usually we have no data or we have only a sparse label data. I'm giving two examples of the supervised learning and to see what the issue behind that and how we move from the supervised to unsupervised or weakly supervised learning. So for example, this is a publication at 2022 at the Technical University of Munich, Deep Learning Methods for RANS Simulation of Airfoil Flows. So they use a UNet and they have a bunch of airfoils and try to predict the velocity and pressure field around those airfoils. So it was a supervised learning work. Another one is what I presented last year in for your research group, a point cloud deep learning framework for prediction of fluid flow fields on irregular geometries. So we published it in the Physics of Fluids. It has been recognized as the editor's pick. And again, this work was based on a supervised learning fashion. And we published it in 2021, and during the last year, it got 34 citations. People in our community become interested in this work. But anyway, this was supervised learning. So I'm trying to explain supervised learning in a very simple example to see what the issue is that. So I said that imagine we would like to obtain the velocity field for example, 1,000 airfoil, and each airfoil has a different geometry. So in supervised learning, what we usually do is that we take 3 steps. At the step 1, we obtain the velocity field for 900 domains, for example. It is just a number, right? Using a numerical solver, using CFD solver, or in a lab experiment, or if we have data somewhere, we can use those of data. In step 2, we train the network using those 900 domains, which usually we call it training set. And then, okay, at the beginning, we had 1,000 domains. We use 900 of them for the training. And now our neural network has been trained. So in step 3, we predict the velocity around those 100 domains using the trained network very quickly. So this is the general story of supervised learning with this specific application. Then we have a bunch of domains with different geometries. But what is the issue is that step 1, we need sometimes producing plentiful label data, which is computationally could be expensive, or sometimes label data are not even accessible. They don't have access. So that's one of the main challenges with supervised learning in this specific application for computational mechanics. What is our goal here is to remove step 1. We would like to design a neural network to predict the solution on multiple domains, but without plentiful label data. So essentially, we would like to remove step 1 and just have 2 steps, step 2 and step 3. Train the network on those 900 domains, but here on these domains, we have, let's say, just a sparse observation. And in step 3, we also predict the quantity of the desire on the rest of the geometries. So the first thing that comes to mind that when we wanted to use just a sparse observation or somewhat unsupervised or weakly supervised learning is a physics-informed neural network introduced by Crunch Group, a research group. It's published in 2019, and it got lots of attention, more than nearly 2,400 citations in 2 years. It's published on the JCP. So I'm explaining the idea of the physics-informed neural network introduced in that JCP journal paper by a simple example. I have taken this picture from this source. I think this journal paper also published by your research group. So imagine that we would like to solve just a heat equation, conduction, for example, and we have spatial coordinates and time. So we are using a fully connected network, and then we are using automatic differentiation to define to get the equation of interest, the partial differential equation that describes the physics. And in the last function, we use governing equation boundary condition, initial condition, and some sparse observation if they are applicable. So instead of using just a mismatch between prediction and ground truth, because here we don't have plentiful label data, we use the governing equation as a loss function. So now, but coming back to this slides, what was my goal? My goal was to design a network that predict the solution on multiple domains, right? Not just one domain, but also with the sparse observation, sparse data. So definitely the physics inform can help us with sparse data, but how about the multiple domains? So I'm trying to explain it by a simple example. So imagine that we have more than one geometry, for example, two geometry I have here. So we can see that, imagine we have 2 points with the same spatial coordinates, for example, 6 as a x and 6 point-ish as a y. But one of these points exists in the domain and one of them is even outside of the domain. So this network cannot handle this situation, right? I cannot fit both geometry simultaneously to the network. Or maybe there is we have a common points between two domains, for example, 4 as a x and 7 as a y. But maybe the solution at this point would be different at these two domains. So again, the question is that, can this network handle this situation? And the answer is no, because this fully connected network cannot capture the geometric differences between these two geometry. And it's not ideal, because if we have a multiple domains for each geometry, we need to retrain the network, essentially. So this issue addressed in a Geonet journal paper. It's published in JCP, and they talk about this issue and they try to address this issue by proposing some strategy. They said that, okay, imagine we have a multiple domains, multiple geometry. We can use an encoder in convolutional neural network to make a difference between each geometry. And then instead of using automatic differentiation, they use non-trainable filter, which represent a finite difference stencil, to solve the equation. In fact, they first discretize the equation using some finite difference scheme, and then in the CNN, they use some non-trainable filter to represent that stencil. But how about irregular geometry? They said that we can use elliptic coordinate transformation for irregular geometry because CNN works just for Cartesian grid types. And this picture shows the structure of the Geonet. So we have a multiple input. We have CNN. Because we have encoder in CNN, we can make a difference between each geometry. The yellow box shows the fixed non-trainable finite difference filter. And then they have a residual of the governing equation as a loss function, and they train the network in that way. What is the issue with this strategy? First is that when we use a finite difference scheme, then all the associated issue becomes visible. So for example, order of the accuracy, or also if we use high order accuracy, we would have issue near the boundaries. And also for the irregular domains, if you wanted to use elliptic coordinate transformation, before training and after training, we need offline efforts. And for some mathematical reasons that they explain in their journal papers, their methodology cannot handle more than 5 zero continuous boundaries. And this is the most complicated example that they solve in the journal papers. It's a vascular geometry. It describes the left and right boundaries for different parameter of the S. This is the 3 example of the physical domain. They use the elliptic transformations to transfer them to the reference domain, and they compare the solution of the CFD with the solution of the PhenoNet for the pressure and velocity. So you can find the details in their publication, but here is our proposal. We say that, okay, here we have a fully connected network, which seems this is the main issue. It's not able to capture the geometric variations over multiple domains. Instead of using just a fully connected network, let's use PointNet. And PointNet was introduced in 2017 in Geometry Computing Lab at Stanford. It is originally introduced for the computer graphics application, classification, part segmentation, etc. And it also has become very popular among the computer science community. It's cited nearly 7,000 times. Okay, so I'm going to give you some details to see how does it work for the purpose of the physics informed PointNet. So imagine I have a domain, or we have multiple domains, and we wanted to solve some specific equation. For example, in compressible flows, we have a continuity and momentum conservation. So we say that, okay, so we can represent each domain as a set of points. So if you have if I have a domain, I can represent it as the endpoint. So for example, if it's 2D, x1 becomes just x1 and y1 because it's the 2D, and n is the number of the points in each domain. In the next step, we approximate the geometric feature of that domain by a global feature such as G, which takes the maximum, is the max pooling of some shared MLPs of the input points. So H is just shared MLP. I will explain it in the detail, but for now, at this step, we capture the geometric variation. Now we have some output, for example, velocity at some point I. So, which is the output of the network, and it's a prediction of the network. So this value depends on the spatial coordinates at the same point, but also the geometric feature of the whole domain. So,
sorry,
for example,
Ali, can I ask a question about this?
Sure.
This is Nat Trask from Sandia. So for the internal layers, when you go through max pooling, right, you get a coarsening of your point cloud, but do they have a coordinate associated with them, or is it just, it's just abstract, right? Like you don't get a concrete interpretation of this as like a hierarchy of point clouds. Is the question clear?
So I will explain this line in the next few slides, so maybe then it becomes more clear. Yeah.
Okay. Thank you.
Thanks. Yeah, but okay. So what is the next step? The next step is the taking the automatic differentiation of the output with respect to the input, because, for example, I'm interested in the residual of the continuity equations. So because, for example, the velocity u depends on both the spatial coordinates at that system and at that point, and also g of x, then del u del x also depends on g of x, and g of x depends on the whole geometry. So then we have a residual of the continuity, for example, del u del x plus del v del y. And the loss functions becomes, I mean, here I have only written the continuity term, but we could have other terms that represent the physics, definitely. So this is the summation from 1 to m, and m is the number of the geometry. So the weight of the physics-informed PointNet is updated based on all the domains at each epoch during the training. And each rj different from another one because gx is different for each domain. Okay, so now I'm going one step further in the detail, and I wanted to explain this line g of x, which is the maximum of the hx1 blah, blah, blah. So what is the philosophy behind that? So it's actually represent one of the feature of the PointNet, and consequently physics-informed PointNet. So imagine we have a 2D domain, and the 2D domain is represented by a bunch of x and y, right? So I have written here just 1 to 4. And now I'm permute the input, right? So just x2, y2, x4, y4, x3, y3, x1, y1. This is exactly the same geometry. But if I come back to here, because the input is just a vector, right? So if I permute the input vector, the output should not be changed exactly here. So how PointNet handles this situation using share MLPs and also using a symmetric function. Actually, PointNet has to be invariant to n factorial permutations. So that is why it's used the max function, because it's just a symmetric function. It could be a summation or average or minimum, but I mean, PointNet originally use max function, and we also use max function. And also H is a shared MLPs. We apply the same actually MLP to each input point. And this is the reason behind representation of the G of X. Because it has to be invariant to a permutation of the input vector. And just as a note, the shared MLPs are not a dense layer. So sometimes people maybe got confused by that. And if you are interested in the implementation of the shared MLPs, you might take a look at the source code of the PointNet. And also there is a manuscript networking network that explains the shared MLPs. This is in the archive, and it's cited more than 6,000 times. So now the issue that we had in the past has been resolved conceptually. So the network can get more than one geometry. It can handle uncommon points between these between two geometries, or the solution might be different because the solution at each point would be also a function of the global feature. So in terms of the PIPN, we say that, okay, imagine we have a two set phi and set psi. So set phi has m domains, set psi has L domains. So for set phi, we have some sparse observation of the PD solution. So what we do is that first we train the PIPN to solve the problem of interest on the set phi, and then once we train that, first we could obtain the solution on that set, and also we can use that set to we can use the trained PIPN to also obtain the solution of the geometry over the set phi quickly, because when we were training PIPN on the set phi, we automatically also train the PIPN on the geometric features, right? So we would say that if the set phi contains some unseen geometry from seen and unseen category with reference to the set phi, PIPN should be able to also obtain the solution on the set phi.
Ali, I have a question here.
Sure.
So unseen here means outside the distribution or within the distribution of geometries?
Set psi.
The unseen, for example, let's say we have a square, right? And we make a rectangle and the put limits on this on the edges of the rectangle. So unseen could be a geometry that you didn't use in the fit test, a set, but also unseen could be a geometry that has now edge 50 and 60, and that was way outside the bounds of your box in the training set. So that's outside the distribution. Do you consider in set C both, inside the distribution and outside the distribution?
Yes, and I have I have an example that I'm going to show you that. Yeah, I mean, we can see how we consider set psi.
Okay, great.
Thank you. So we consider a classical fluid dynamics problem, natural convection in a square enclosure with a cylinder. So it's a hot cylinder inside of the cold cylinder. So we suppose that the inner cylinder could have a different shape and different pose, different orientations. So also we imagine that we don't know the temperature distribution on the inner cylinder, the surface cylinder, on the surface of the inner cylinder. Here is the set of the geometry that we produce. It's the equilateral nonagon, octagon, heptagon with different orientation. So as the professor mentioned, that we consider two sets of psi. First, unseen geometry from seen shape, and again, and another set, unseen geometry from unseen also categories. So for the first step, I suppose that here we have 135 domains. So we randomly split into the set phi and psi. We say that, okay, we have 108 domains in the set phi, and also we have some sparse observation in the sensor location for that set. And for the rest of the domains, we have no observation. We put them on the set psi. But here, the difference is just the orientation. In the next, I mean, first I try on this set of psi, and then I change that to totally new shape. Okay, so, and here is just the sensor location for three example of set phi. So loss function is conservation of the mass, conservation of the momentum, conservation of the energy, velocity boundary condition, which is just no slip boundary conditions, and temperature boundary condition for the outer cylinder, and also a sparse observation of the velocity, temperature, pressure in the sensor location.
Hello, Ali. This is Lulu from Japan. I have one question in the slide. So here you also added the sparse observation. How important is this sparse observation for the learning? So ideally, I would think so. Ping is unsupervised, right? We can learn the ping without any observation, but this could be ideal case. So in your case, is this important, or we can remove this part?
Okay, actually, based on my understanding from PIN is that it's useful for both forward and inverse problem, in a sense that sometimes we don't have a boundary condition, but we have some sparse observation from inside of the domain, and we can use that. For this application, we have a sparse observation. I have another test case in my manuscript that we don't have any sparse observation from inside of the domain. So you might take a look at that.
I think Ali here, you don't have a thermal boundary condition like a case that we consider in our paper for heat transfer. So that's why you need a collection of sparse observation for velocity and temperature and pressure. If you had, I think Lulu is asking the question, let's say you had prescribed, let's say, Dirichlet boundary conditions on the shape of the unknown shape that you're changing. Would you still need sparse observations?
Okay, I tried that, not specifically for, this is the Rayleigh number of 10 to the power of 5. I tried for the Rayleigh 10 to the power of 3, and it was very slow. I mean, it was slower than CFD solver. So I imagine that it's not really, at least at this, because one of the challenges that is because we have a huge number of geometries, then the training process also can take longer than just training the geometry on one domain.
Okay, so it helps. It helps even if the problem is well posed. It helps because you have a plurality of geometries.
Yeah.
Okay. All right.
Okay, thank you.
So here is some results. So prediction, the first row shows the prediction, the second row shows the ground truth for the velocity in X direction, velocity in Y direction, pressure, and temperature. This is one geometry from the set of C. This is another one, different geometry, different pose. Here is the absolute pointwise error distribution. When the quantity of the interest, the error of the quantity interest becomes maximum or minimum. For example, the panel A shows the absolute pointwise error for the velocity in X direction when the relative error becomes maximum. Maybe I should.
Sorry. So this one is the training data set, right? This is the training set, the 108 training.
This is the set C that I have a sparse observation rates.
Yeah. Used for training. Okay. Yes, I see.
Okay. Now the set psi. The set psi contains the same shape but different poses, different orientation. For the set psi, we didn't have any sparse observation. So here is 2 examples of the outputs. And also here is the absolute pointwise error distribution for velocity, pressure, and temperature field. And the table, in the table we
Sorry, can you go back to that? I just want to understand, because there's a question about how far you're pushing it out of distribution. And this is, am I understanding you correctly, that this is just like a different rotation of that polygon?
Yeah, here is a different rotation. Next, I will move to the next, the new shape.
Because the solution is basically identical. You know, for like a low Stokes, for a low Reynolds number problem like this, right? There's not a huge difference between these. Is that right?
The Rayleigh number is 10 to the power of 5. So I think the nonlinear term.
No. The solutions will change. The solutions will change a lot. It's a gravity in the vertical direction. So there's no azimuthal symmetry.
Oh, there's great. Okay. Yeah, it's just hard to see by presenting the error. I can't see.
It's a thermal plume. It's a thermal plume. It's a natural convection.
I see. Okay. Thank you.
Sure. So for each U, V, P, and T, and also the temperature specifically on the inner surface, we compute the relative error, average, maximum, and minimum. By the average, I mean that we take the relative error at for each domain, and then we take an average over the whole set. So if we look at the average one, we can see that the maximum error happens for the velocity. For the U, it's nearly 10%. But if we compare, this is for the set phi, where we had a sparse observation. And now if we compare with the set psi, we observe that in the average, the relative error increases. And it is somewhat makes sense, because for the set phi, we had some sparse observation, and also the PIPN has been primarily trained on that set. The huge difference happens for the temperature distribution on the inner surface. So for the set phi, we had 2.2% of the error, but for set psi, it becomes 7.4%. But now, okay, so I have also the temperature distribution. Theta is the reference angle. So from 0 to 2 pi, I plotted the temperature distribution over the set phi when the relative error becomes maximum or minimum. And also for the set psi, the red one shows the maximum error, the blue color shows the minimum error. We can see that the maximum errors happens in the corner of the polygons. Okay, so now we come back to your question that how much set psi will change with respect to set phi. So here I set the set psi as with two new geometry, with two new shape for its cross section, circle and a hexagon. So before that, we had just the heptagon, octagonal, and anagonal. So let's see the result. Here is the prediction for the circular inner cylinder, the prediction versus the ground truth for the velocity, pressure, and temperature, and also for the hexagon. And in the next one, I have also plotted the absolute pointwise error for these two new shape. we can also take a look at the error analysis. So definitely this time the error increases compared to the previous set of the psi, when the psi was the same shape but a new orientation. So the maximum error happened for the velocity. It's close to 60% relative error. And here we have a temperature distribution, theta from 0 to 2 pi for the for the circular and hexagonal inner cylinder. We observed that for hexagonal we have a higher error, so we can see that in the table. It's just 3.5% for the hexagon and then 1.1% for the circle. So now we introduce PIPN. We might also ask some new question. For example, we had there was a publication when and why PINN fails to train. So the question would be that now, because we have a shared MLPs and also we have a max functions, so how the error analysis change? How we can answer this question for physics-informed PointNet? Another question could be in terms of the parallel computation. So this is a journal paper published by your research group. It's a domain decomposition for physics-informed neural network. Then we have only one domain. Now we have multiple domains, and also the networks take care about the geometry of the whole domain. So how, from a software engineering perspective, how we can define a framework for do the parallel analysis and the domain decomposition for physics-informed PointNet. So our plan is to extend the problem to the 3D test cases, and also we consider unsteady problem, consider different applications for compressible flows, solid mechanics. And the manuscript is on the archive. If you are interested, you can take a look at that. And in the summary, we propose physics-informed PointNet as a novel physics-informed deep learning framework. So PIPN can obtain the solution on several irregular domains by training only once, and it overcomes the shortcoming of the regular pins that they need to be retrained for any single new geometry. And we showed an application of the PIPN for a thermal field. Okay, at the end, I would like to do a short advertisement in another publication that we have. I thought that maybe some of you would be interested on that. We work on the prose media, and we use PointNet for the prediction of the permeability of the prose media. We point cloud deep learning of prose media for permeability prediction. We publish it in Physics of Fluids. It has been recognized as a feature article. So the story is that usually in prose media, people represent it using the 3D image. We represent it just as a set of points clouds. So if you are interested, you might look at that. And if you had any question, I would be happy to answer. Thank you.
So can you say a little bit more about that? Where's the how do you choose the points in that point cloud?
Okay, sure. So the idea is that in the prose media here, imagine we have a porous space and grain space. So imagine that the red color shows the grain space, a blue shows the porous space. For example, the flow just can't go through the porous space, the blue color. And if we represent the prose media as an image, then imagine that each side has the size of the 64. Then just for one cube, the size of the data becomes 64 times 64 times 64, it becomes 200,000. How we represent as a set of the point in the manuscript, in the journal paper, we show that we don't need the whole geometry. We don't need the whole pore and grain space. We only need the boundary between the pore and grain space. So we recognize the boundary between the pore and grain space, and then we represent the boundary, which is the surface, as a set of points, which has X, Y, and Z. So here I have 4,000 points, and each point has a 3 dimension. So 4,000 times 3 becomes 12,000. So in this way, we could dramatically reduce the GPU memory requirement. But definitely, when you have a new representation, you cannot use the convolutional neural network. You need a new deep learning framework, which is suitable for the point cloud. We use the PointNet, but this is a classification branch of PointNet, not the segmentation. In the physics-informed PointNet, I use the segmentation branch. Here is the classification branch. The input is the set of points, the output is the permeability, a scalar number.
Thank you, Ali. That was great. You have lots of people watching, 46 people, and it was really good. I have a question first, if you don't mind. Have you tried to compare with the Phi GeoNet of Notre Dame, the one that you refer to for those simple shapes, which are parametric shapes, so therefore you can, I think you could do much better than them, right? Or at least you can be very competitive and still more general.
Yeah, I can. If I come back to
this one, yeah, this class of geometries, yeah.
But I think they cannot handle more than 5.0.
Yeah, no, I was thinking like you can benchmark this code. If your code is on the web, we can do it ourselves. Is your code on the web?
My code is not, but the PointNet code is available, and what I have done is just to define a loss function. I did, in terms of software engineering, it's not a. I think it's not a difficult task.
Okay. The actual question actually was, you can formulate this also as a domain adaptation approach. Have you thought about this?
Domain adaptation? No, I will think about that.
Okay. So data, have you seen people who are changing the domain?
No, they haven't. Like in any of the papers that I have read, nobody has worked on domain adaptation where they have changed the domain size, domain shape or size.
What do they change when they in the domain adaptation?
Normally, George, in the domain adaptation papers, they have worked with vision problems, and they change either the location of a hole over the location of like a image or one particular point over the whole domain, or they would actually change the function and they will predict another solution field, but that is specifically to image vision. Changing the domain like this to get the solution of the PDE changed, no.
Okay, so Ali, congratulations. Any more questions?
Ali, have you looked at the stability? Right, so there's a question now that you have this model and you have like a parameterized model in terms of the geometry. There's a question about doing like inverse problems and design problems where now you want to embed this in another problem, right? Where you want to say like give me the optimal geometry which can solve to like minimize drag, for example, if you're talking about airfoils or something like that. Have you looked in that direction and whether this is like stable enough to embed in another problem like that?
Yeah, I see your point. Actually, I thought about that, but I mean, in practice, I mean, yeah, it's. I think that no, I in practice I didn't touch that. But definitely, it's. I think it's a ideal point, right? It becomes a framework that you can use in the industry. That I mean. You can get output, and then based on the output, you can modify geometry. Again, maybe perhaps using some other networks, for example, as you said, maximize or minimize a quantity of interest.
And do you need parametric representations of the geometry to do this? I missed that part. Like, for example, like say it's a rectangle, you have like W and L for the width and length of the rectangle. Do you need that sort of description of a geometry?
No. The only thing that you need is to represent your geometry with a set of points.
Right, yeah.
Right, exactly. Yeah.
That's the point, Clark. Ali, what not ask, actually, you had it in your second slide, I think, the design loop for the airfoils for the car. You're sort of alluding to that, yeah, and the airplane. Yeah, you had that, yeah.
Exactly, yeah. Yeah, I mean, this is what this is building toward, right? And super exciting, really interesting. Just curious if you've gotten here yet, or if it's kind of like the long-term objective.
I mean, Ali, I think the issue is, and you're pretty honest, and you show here L2 errors and so on, but if PointNet can go beyond computer graphics and give accuracy, which is respectable, because in a simulation like this, you know, if you have a 10% error, that's how much you try to improve the drag to have an advantage over the competition. So you really have to have a high fidelity in the geometry. I work with, actually, I was talking to Mercedes-Benz on Tuesday. They want exactly this problem. They asked me how you can do pins for different geometries and do it fast. So they can evaluate their drag, the drag force on the different designs that they, in preliminary design, before they decide if they proceed with the design or so. So this is a great tool. It's just that a 10% error may not be good enough. That's what I'm saying.
Yeah, I see your point.
But if it's probably a couple of percent error, even upper bound 5%, could be very useful in this application that you show here, both for the cars and the planes.
Yeah, I think here I use the original PointNet, and it is introduced in 2017. After that, people introduce in computer graphics lots of other PointNet versions and they show that there are some improvement compared to the original PointNet. I didn't use those versions. I just used the basic version of PointNet. So that might be a solution. Try different newer version of PointNet to see how the error changes.
Yeah, that's good.
Excuse me, can I ask a question here? Hi, this is Panastinis from Pacific Northwest National Lab. So I see that there is I don't know if it's severe, but there is a trade-off here. You go from a shape that is in 2D, and now you represent it as a point cloud, right? So
yes.
So the function that you learn, which is the velocity, before it was a function of x and y, and now it becomes a function of a huge dimensional space, right? Which is equal to xn, right? N. So that immediately creates an issue about how are you going to learn accurately the velocity, which is expressed as a function of so many different, in so high a dimension. And from what I see in your results, what you called psi as unseen category, where you tried it on octagon, and what was the other thing?
Circle and hexagon.
Circular and octagon. these are not actually very far, topologically at least, from the phi set that you trained on. So I think that you're getting probably, you're getting similar errors between phi and psi because the psi, what that you call unseen category, is not actually far away from the phi. So have you actually tried a different geometry like a star-shaped domain? Because there, that issue that I pointed out about the velocity being a function of such a high dimensional vector could actually become an issue there.
Yeah, okay. So, I mean, one point is that, I mean, the beauty of the PIPN is not just about the psi-phi. I mean, even if you just remove set psi, just think about set phi, still the regular pin cannot do that. So, I mean, if I put a star, no, I mean, the prediction would be bad. That's the simple answer. But if you think that you might be interested in the physics-informed PointNet, I believe that the main advantage comes back to set phi, that you have a bunch of geometry, you have some sparse observation, and then you wanted to have just one network to obtain the solution on that set phi. If you have some set psi, then you can use that. But even if the set psi in the geometry in the set psi would be very far away from the set phi, it doesn't mean that the PIPN is not useful.
Right. I understand that, but my question actually also goes back to what Nat asked about design, that sometimes in design, if you want to stay very close to the original design, then fine. I think this will work if you bring down the error like George suggested. But if you want to explore a design space further out, I don't know how much you can use this approach, which uses only points, a point cloud.
Yeah, yeah, I see your point, and I believe that this is the first step. So in the future, hopefully, we can improve it in other aspects. But in terms of the point, usually in the CFD, when we wanted to solve a problem, we use some grid vertices, right? So we discretize using finite element, finite volume. So you can think about the point cloud as a location of the vertices. So you can have the density distribution of the point cloud doesn't have to be unique everywhere. Somewhere you can have some fine points, other parts you have coarse points. You can think about that as the point cloud representation is the grid vertices representation of the mesh generator.
I agree, but the whole, I mean, one of the main advantages of PIN was that somehow it was trying to free us from grids. But now by using the point clouds, because you are actually evaluate a function, which is the output, which is a function of the grid points, you bring back this issue of having, like you said, a grid, right?
Oh, you don't have to use the grid.
No, it's not a grid, but it's a cloud point. It's a point cloud, sorry. You get a function which is a function of the point cloud, right?
Yes, it depends on all of the points. Yeah.
Yes. So you cannot, for example, compute the velocity somewhere else, right? Because your output is a function of the point cloud. So you cannot do interpolation to get the solution somewhere else in the domain. Maybe you don't need it, but all I'm saying is that you get an advantage, which is that you can actually maybe describe more complex geometries, but at the same time you give something up, which was in the original pins, for example.
Well, honestly, I don't see the issue. I mean, compared to the pin, at least the regular pin. So in terms of the interpolation, we have another test case in the manuscript that we have some points outside of the near the domain, but outside of the domain. So you might also take a look at that. Also, the framework can do some interpolation outside of the domain. But in terms of the generalizability, that how much those sets can have variation with respect to each other, I agree with you that there is a room for improvement, definitely.
Okay, thank you.
I had a
Sure.
question. Hello.
Yes, go ahead.
Yes, hi, I'm Vivek from Professor Karnidakis group. In your paper you uploaded in archive, I saw that while solving incompressible flows using PIPN framework, when you drop the Dirichlet pressure boundary condition in the loss function, your error in prediction of velocity fields increased by almost 45%.
For which test case?
It is in page number 12, section 4.1.2. So
4 point. Actually, I don't have. I mean, this was for the thermal fluid. Okay, I think that the story of the pressure is that if you don't have any information about the pressure, no boundary condition, no observation, yes, definitely the error increases also for the velocity.
But you dropped the Dirichlet pressure boundary condition in which the loss term was P minus P ground truth at the boundaries. But for fluids, the gradient of the pressure is affecting the flow rate. So why would dropping a Dirichlet pressure boundary condition in the loss function cause a sudden jump in velocity prediction by 45%? That was my question. Yeah, thank you.
Yeah. I think you are talking about another test case which we didn't discuss here. So for that test case, we discussed that, okay, because for the Navier-Stokes equation, for the incompressible flow, pressure is an implicit variable. So we just investigated that if we don't have any information about the pressure, how the solution changed. And then, as you said, we observed that the error for the velocity also increased. But what was interesting for us that the gradient of the pressure would not change that much. So somewhat we observed that the PIPN can conserve the gradient of the pressure, and it's not, and it makes sense because in incompressible flow equation also we have the gradient of the pressure, not the pressure itself as a explicit variable. We investigated that. Yeah.
Thank you.
Sure.
I think other, do you want to add to your, you made a comment, you made a comment about the scatters, yeah, and geometries.
Yeah, hi, Adal from Crunch Group. We had a paper back in the day about what some data said about trying to find a scatter in the domain. And then I want to summarize like all the discussion that was there before. I think Panos said a lot of very important things. When you try to figure out how to optimize some component like airfoils or a wing, the method should be very robust. And what the comment that I received was like, for example, octagon, or sorry, a circle is a infinite edges polygon. Okay, so I think Panos said, and it's very important that all of the test cases that you tested are very similar. Like the shapes are very similar. in the paper that I put there, we tried to tackle a problem with arbitrary shaped polygons, where we just completely randomize the edges, the angles between the edges, everything like that. And we also created non-convex polygons. And to solve this challenge, basically what we did is use some other methods from image processing that fit here. And you can see there, maybe it can give some intuition on how to use your method. Still use the PointNet and the physically informed part, but maybe add a term that takes in account the domain points that you're trying to change every time you are changing the component. And use this as a kind of a regularization term or a constraint for the network. This might be helpful for you to get like more robust inner cylinders.
Yeah, I mean, definitely I am interested in that. So please send me the papers, and then I definitely take a look at that. Thank you for your comments.
Perfect. I put it in the chat, and if you have any questions, feel free. I'll be happy to discuss it further.
Sure. Thank you very much.
With this, we'll proceed to our next speaker. Professor Mhaskar, if you could share your screen. You are muted. Professor Mhaskar, you are muted.
Unmute.
Yes.
Okay.
Maybe I'll introduce you to our group members. So our next speaker today is Professor Hrushikesh Mhaskar. He has been with the Claremont Graduate University since 2012, and he's a research professor of mathematics. Prior to that, he was a faculty at California State University, Los Angeles. He holds a PhD in mathematics, MS in computer science, and an MS in mathematics from the Ohio State University, and an MSc in mathematics from IIT Bombay. His honors include Alexander Humboldt Fellowship, John von Neumann Fellowship at the Technical University in Munich, and the August Wilhelm Scheer Visiting Professor at TU Munich. His area of research is approximation theory and harmonic analysis. He has done a lot of work in the theory of weighted polynomial approximations on real line, in particular, making deep contribution in the area of orthogonal polynomial expansions and application of potential theory of the study of orthogonal polynomials, also known as Freud polynomials. With this, I may want to pass on the screen. So you may want to start, Professor.
I also want to welcome Hrushikesh, who is not new to Crunch Group. He spent some time with us, some data before you came. That's why. But Hrushikesh is a good friend of Crunch Group.
Yeah, definitely. I was surprised that she had to introduce me in so much detail. Anyway, thank you very much, George, for inviting me, and Somadatta also for arranging everything, and all of you who decided to attend. So this is one of the most complicated paper I have ever written, and I hope I won't bore you, or otherwise you will enjoy a good nap anyway. So here is the statement of the problem. We have two matrix spaces, and we have a compact subset of the domain space. And then we have a continuous function. And I will talk about the smoothness of this function later on. And then the idea is that we have a finite amount of information about this function, which I will call operator. And then we want to find an efficient method to approximate this script f. Also, we want to estimate the degree of approximation. So here is the motivation. Probably this is not necessary for you because you are more into it than I am, probably. But still, I think after a whole hour of talk, some people might want a break. So it's a good idea to state this motivation anyhow. So The first motivation is system identification problems. So we have a general dynamical system which is given by this formula. And then we have to find an output signal Y when we are given an input signal X. And from this data, we want to identify this system script F. I don't know if people can see my cursor here.
Yes, we can, Professor.
Okay, good. So it seems like it was a hot topic in the 1990s. There are a lot of people who worked on this. Narendra Parthasarathy had a big paper about this on using neural networks, and then Sandberg and Moda and also Dingankar introduced me to this problem. And there is also a nice paper by Chen and Chen, which everybody in this group is familiar with, where he addresses approximation of these things by neural networks. But his results are only possibility of approximation, the universal approximation theorem. He does not say anything about the number of parameters to achieve some approximation. Then there is another area which I would like to get into, that's the uncertainty quantification problem. So we, for example, in this quite often cited paper of Cohen, DeVore, and Schwab, they are looking at this problem where a omega x is a random function. And then they are interested in finding out the expected value of this u at x. So one of the ways to think of it is to think of this expected value as a function defined on the space of these functions A. The advantage of doing this is that instead of solving one problem, we are solving all the problems at once. Then this is also the case made in a paper by Nelson and Stuart, and the whole theory probably originated with this paper of Lugin and Karniadakis having to do with PointNet. So we are interested in partial differential equations, and then we are approximating, we consider solution of this differential equation as a mapping from this boundary condition to, the initial condition to the solution U. Of course, one can also think about the inverse problem where you know the solution U and you want to find A. That also falls in the same abstract framework. Then here is another application which I have not seen in the literature very much, that we are given a series, a whole set of time series. And then these time series are modeled by such dynamical systems. And we don't know what the f sub j is. So if I want to do system identification, then the problem is to find this f sub j. If I want to do classification on time series, then I'm looking at a whole class of functions f sub j, and I want to treat the class label as a functional on this whole class of functions. Okay, so I will start with some background work on this, which I did more than 25 years ago. So here is the setup in a simple example. Our metric space is the L2 of the Q. Then by P sub m, I will denote the orthonormalized Legendre polynomials. So the integral, they are orthogonal, but the integral is 1. And then I look at the orthogonal basis for this space consisting of tensor product Legendre polynomials. This is the compact set which I'm interested in, which is really just a Sobolev class for this function. And then the class of operators which I'm interested in satisfy the Lipschitz conditions. All of this comes from these papers by Sandberg, and I think probably Chen and Chen also assumes such a condition. The advantage of this condition is that if I approximate my f by some Fourier expansion, and then evaluate this script f at this Fourier approximation, then I get a function of m variables, m plus 1 to the q variables. And now I have reduced the problem from approximating functionals on this Banach space to approximation of multivariate functions, which is in theory a known problem. So the problem here is so that going back, it's a problem on approximating on Euclidean space, but the dimension is extremely large. So the M has to be large in order to approximate my input function accurately enough. And then the D will have to suffer a tremendous course of dimensionality. So we need a very good approximation result in multidimensional case. The only result I could find was an old result by Newman and Shapiro. And this result says that if you are looking at a ball of radius 1 in Euclidean space of dimension D, and F is a Lipschitz continuous function on that set, then there is a polynomial which satisfies this bound. This part of the bound is the usual expected bound, but generally in approximation theory, the constants depend upon the dimension. And then we don't know how they depend upon the dimension. The beauty of the Newman-Shapiro result was that this constant is an absolute constant. It has nothing to do with D or N or M or anything like that. I think that constant is 6 actually, but I don't remember. So the other ingredient was so that if I have a polynomial approximation, then I can also write down a neural network approximation if I want to. It has nothing to do with the function being approximated or anything like that. We just synthesize every monomial using such a network. And then if you have a polynomial, you express it in terms of monomials, and in theory, you have a neural network. So with these two ingredients, then the idea is like this, that we have this, I'm sorry, this script F should be in script, this is an operator. F is my input function. Then I look at the Fourier coefficients of this F, the first M of those, up to the first M degree polynomial of those. And then it's quite easy to figure out from the definitions that the difference between this object and this script F evaluated at the corresponding Fourier series is bounded by this. And so together with the Newman-Shapiro theorem, it means that if I apply my polynomial operator to this little f, then this is the bound I get. Once I have a polynomial here, then I can construct neural networks. It has exactly the same degree of complexity.
Can you remind, Hrushikesh, can you remind us the S and the Q? Because I'm lost a little bit. The S and Q is...
So we are
okay, so yeah, Q is the tensor product, yeah, the number of polynomials.
And S is the Sobolev index.
The Sobolev index, yeah, sure. The regularity, yeah.
And there are lots of F's here. The script F is supposed to be the operator. Capital F is supposed to be the input function. And little f is supposed to be a function acting on the Fourier coefficients. And then this Pn is the operator given by Newman-Shapiro theorem.
Yes, thank you, thank you.
So, so then there is a balancing to do between this D and this, if you want to, because at that time I was interested in the number of neurons in the neural network. And then it turns out to be such a rate of approximation. That doesn't look good at all. It just log n, and then there is a course of dimensionality. And so then I begin to wonder, did I do it right, or is this the best we can do, or what can I improve? So the way to answer such a question is the idea of nonlinear widths. So we have a compact set of a metric space, and we select some parameters on the function. Oh, I'm sorry, this I should have corrected the picture, but it would have taken me another hour to do this. So this script P is supposed to be script I. And then we have an algorithm which takes back from these parameters to some approximation. And then this is the distance which we are interested in. We don't know what this little f is. All we know is this prior, that it belongs to this compact set. So we have only to look at the supremum over all the f's on this compact set. That's the worst case error. which can be done using this parameter selection and this algorithm back. The nonlinear width is defined to be the infimum over all these clever parameter selection methods and approximation reconstruction algorithms, provided this parameter selection or information operator is continuous. If you don't have it continuous, then you get 0 as the width. Okay, then it turns out that the class of Lipschitz operators, which I was looking at, and the, in this metric of uniform norm on this compact subset, which is the unit ball of Sobolev class, the width is at least log n to the minus s over q. So apart from this log n factor, this is the best possible. It's not possible to improve upon my bound. But the bound is not good, so we have to improve upon it. And so it becomes a challenging problem to improve something which cannot be improved. Okay, I thought the problem was sinking in my mind for last 25 years or so, and then I was wondering off and on, but did not have too much of an idea. But then after I got in touch with this crunch group, and then I realized that it is a hard problem to work with, then I started more earnestly to work on it, but it is still one of the most complicated papers I've ever written. So anyway, the first step is the problem reduction. So we have this metric space and we have this y now. F is our operator or nonlinear function. We are interested in approximating on this compact subset. And of course, if this is a continuous function, then it will be contained in another compact subset of y. We don't have to know the exact image. We just have to know that it is contained in some compact space. In the back of my mind, the kx and kys are the Sobolev classes. But in this abstraction, we don't need anymore to talk about L2 or LP or whatever. They are just metric spaces and compact subsets. We need the parameter selection or information operator, which will map this metric space to D parameters. In the back of my mind is this D is the degree of the polynomials in a high dimensional space. And then we need an algorithm to reconstruct the function back. All this, of course, will depend upon the problem, whether you choose Fourier coefficients or the values or some other information. And likewise, the algorithm is also completely free here. Those are not my main concerns. Yeah, well, we just hope that these are chosen somehow so that if I look at the worst case error corresponding to these two methods, then we get something which is not too bad compared to the D width here. That's not the main problem of my current work. So I just assume that this is done and hope that this is done correctly. And likewise, the same thing with Y also. We have this information operator going into some R to the M, and then an algorithm back. And again, we hope that these are somebody has selected them correctly in this sense. Okay, so once more, the problem is reduced to approximating a function of D variables taking values into M variable space. And that function is given by such a thing that I take the information of on my input function and evaluate f of this algorithm. That's my script. That's my boldfaces, and the value will be the information corresponding to the value of the operator at f. So that's a vector valued function on a Euclidean space. So we know in principle how to do such things, except that I did not know how to do it and keep track of all the constants. So pictorially, this is the paradigm which I'm thinking about. This is the input function to my system. This is the information operator, which gives me a point, and in a moment I will explain why it should be on the sphere. That's the pre-processing part. Then comes the main processing, where I try to do approximation of each of these components of the information operator on the image space. And after that comes the post-processing part, where I use this algorithm to reconstruct the value of the functional on the input f. In the DeepNet paradigm, this whole process is done as a deep network using some training. My thinking is that we can split this into 3 parts. These are in my mind some neural networks depending upon, let's say, n neurons. Then each of them has the parameter complexity d times capital N. And then you have to do this m times. So if we do it blindly, then the prima facie complexity will be d times capital N for this part and m because it has to be done m times. That's huge. So, okay, we need some further ideas here. The hugeness of the thing is really the big problem here. The information operator has to take place into high dimensions. We need high value of m. And to get the good approximation also, of course, the network will have to be very large. How can I do this? One solution is to assume some extra smoothness on f. So in my previous work, I had only assumed Lipschitz continuity here because the only result I knew was the result of Newman-Shapiro. And it only dealt with Lipschitz continuous functions. So the big problem here was how to introduce extra smoothness and keep track of the dependence on this D. Okay, another solution to the problem is to do what is now called distributed learning. So you divide this set K, the compact set, into small neighborhoods. And then if you are interested in approximating this object, then you just look at the values of in a small neighborhood of capital F, instead of looking at the entire compact set. But I want to construct an approximation which will achieve both the advantages. I want to use only values in a small neighborhood, but if I can use values in the entire set, then I want the approximation to adjust automatically to the local smoothness of it. The approximation is to be done singly. I don't want to subdivide the kx into small parts first. I want to construct this approximation globally, but it should adjust its approximation degree automatically. Okay, so it is more convenient to go to the sphere for such case. Also, Newman-Shapiro went to the sphere for their theorem. And the construction is pretty simple. You put the Euclidean space on the north pole of the sphere and project every point to the center. And this is the projection operator in formula that gives a coordinate chart for the upper hemisphere. So the notion of smoothness in the Euclidean space translates directly to the notion of smoothness on the sphere using this coordinate chart. Okay, so now I have finished with the problem reduction. I went from the problem of approximating functionals on a compact set to vector valued functions on a Euclidean space, and from there a vector valued function on the sphere. And now I will focus on one component at a time. So now for most of the rest of my talk, I will focus on just approximating one function from a very high dimensional sphere, but only real valued function. Okay. So we need a lot of notation here. By mu d star, I would denote a volume measure on the sphere, normalized to be a probability measure. Then the volume itself is omega d. This is the set of all spherical polynomials, which are really equivalence classes. They are restrictions to the sphere of d plus 1 variate polynomials of total degree less than n. Okay, to find a reproducing kernel for this space, we need Jacobi polynomials. You can find the definition in any standard book on orthogonal polynomials, but these are orthonormalized polynomials with respect to this weight function. And then it turns out that the reproducing kernel for this space is given by this formula in terms of the Jacobi polynomials with these parameters. And here is the reproducing kernel property. Okay, the other main ingredient, starting point of my investigation is the quadrature formula. My insight here is that we don't need a positive quadrature formula, but what we need is Marcinkiewicz-Zygmunt quadrature. So it should integrate all polynomials of degree up to n exactly. But in addition to that, such a stability condition should be there. This object is understood to be the smallest constant which will work here. For all practical purposes, this should be independent of n and d also. Normally, it is just 1. Then I had proved many years ago that there is such a constant, so that when this mesh norm of this C is less than constant over n, then there exists a Marcinkiewicz-Zygmunt measure of order n supported on this set C. There was a mistake in our original proof, then later on together with Frank, I corrected that error. Okay, so this condition just means that if I have a sufficiently dense set on this high dimensional space, then there exists such a measure. Unfortunately, I cannot use this result here because this constant depends upon D, and it's still an open question. How does it depend upon D, or does it really depend upon D or not? But there is a theorem called Chakalov's theorem, and it says that there is actually positive quadrature formula supported on exactly as many points as the dimension of the space, so that this formula holds. And because this is a positive quadrature formula, if you substitute p squared here for degree n over 2, then of course the Marcinkiewicz-Zygmunt inequality will be satisfied with the norm expression to be 1. So this measure is clearly in this space. But the nice thing about it is that it is supported on exactly the minimal number of dimension here, minimal number of amount of points. The bad thing about it is that we don't know how to construct it. But still, this is a theory paper. So again, how to go from polynomials to networks? We have this function phi, which is our activation function. We can expand it in terms of ultraspherical polynomials with these indices. And then it is well known that if you have a spherical polynomial of degree n, then it can be decomposed in this form, where each PL is a homogeneous harmonic polynomial of total degree L. So I take such a expansion and I formulate this phi derivative of P in this natural way, the spectral way. Then it's not difficult to verify that such a abstract network formula holds. So you can think of this as an abstract network where the weights are given by this, and this is then the zonal function network. But it has, right now it is just an abstract thing. If I use quadrature formulas here of the kind which I just described, then this becomes a discrete sum. So it's a zonal function network of this form. The y sub k's are coming from the quadrature formula, so they have nothing to do with P. The a sub k's are coming out of this expression, which in turn depends only on the coefficients of this P with respect to the expansion which I just described. So these are fixed and known linear functionals of P. And then the size of this network is proportional to the dimension of this space. So because I'm talking with the crunch group, I can't resist the temptation of making this joke that I'm making a PIN, theory-inspired neural network, for physics-inspired neural network. Of course, the PIN, I hope the PIN can use the PIN. No. Okay, then comes the very technical part. I want to do this approximation on the sphere, and the main problem is how to keep track of the constants. And so after a lot of thinking and trials and errors, and I could do this only in the mornings, not in the evenings, I came up with this magic kernel. This is the reproducing kernel for the space of dimension d plus polynomials of degree d plus 2 times n. And these are the special Jacobi polynomials. The R is the parameter which will have to do with the smoothness of the function. And this is the factor which will ensure localization. And then I define this operator in terms of the quadrature measure. So it's a finite sum, even if I written it like an integral. The nice thing about it is that this nu depends only on the locations on which this f is sampled. It has nothing to do with f, that's a pre-computation. And the other nice thing to observe here is that it's a universal approximation. I'm not formulating any kind of regularization principle. So this is defined for every f. You don't need anything at all other than the values of this f at the points in the support of this major nu. The degree of approximation will of course depend upon the smoothness of f, and that's the topic of the next few slides. So first, here is the degree of approximation from all polynomials of degree at most n. And then the main theorem here is so that, the basic theorem is so that if this nu is a Marcinkiewicz-Zygmunt measure of this order, then the sigma sub dnr gives a near best approximation. As I mentioned, this quantity is normally just bounded by 1. The biggest challenge here was to come up with this d to the 1/6. And I think there might be some room to improve upon this, but this is how much I can do so far. And this is already a big improvement, and everything else I know about spherical approximation. Okay, there are how to come up with smoothness classes. To my surprise, the notion of modulus of smoothness on the sphere was only introduced in the early 2005, 7, something like that. But the results which you get on the degree of approximation have again this problem that there is an unspecified constant depending upon the dimension. So we cannot use the moduli of continuity here. We need a new smoothness class. And there are a lot of different choices here. They all depend upon what choice to make will depend very much upon how the dimension will enter into the estimates. And so it was not clear. A small perturbation to this would make a lot of difference in the estimates. So anyway, this is my intuition here. This is how we define the Lipschitz class of functions. We can rewrite it in this way. And if my x is fixed, then my f of x is also a constant. Constants are polynomials of dimension less than 1. Polynomials of degree less than 1. So I can also rewrite this formula in this way. So you look at the best constant approximation to f and divide it by y minus x. Okay, so the only difference here is now I want to look at polynomials of degree r, and then I want to look at the rth power in a small neighborhood of x. So that makes it a local smoothness. And if it is the same r for every x, then it gives you a global smoothness. So correspondingly, there is this local smoothness class and the global smoothness class. Then I want to define also analytic functions here, because I noticed in many papers of Christoph Schwarp and Landthaler and so on, that they are interested in analytic operators. My definition is motivated by this ancient theorem. I think it's Bernstein ellipse theorem, which says that this function as an extension as an analytic function to this ellipse. If and only if the degree of approximation has this growth, like e to the minus n rho. Okay, I don't know such a theorem in the context of the sphere, but I can always make a definition like this. So I will say that the function is locally analytic at x if the degree of approximation by polynomials of degree n in a neighborhood of the point behaves like e to the minus rho n. And this is the class for which such things are finite. This is the global class, where instead of having the degree of approximation on a ball, we are looking at the degree of approximation on the whole sphere. Okay, with so much preparation now, the main results are like this, that if I choose this radius of the ball to be like this delta D fx comes from the definition of the local smoothness. Then the globally defined approximation operator has this rate of approximation. This again is normally 1. This is a normalization factor for the compact set. This will also be 1. The important thing is this d to the 1/6. This is what took so much effort and trial and error. And then this is the right rate of approximation. The n-width result already tells us that we cannot improve upon this. Okay, but there is another aspect to this. We don't have to look at the globally defined operator. We could use only the values of this f in a small neighborhood of this point x at which we are interested in. And that small neighborhood is of the radius square root of log n over n. So it shrinks when the degree of the polynomial increases. Okay. So there are 2 variants of this theorem. Likewise, with the analytic functions, if a function is analytic in a neighborhood of the point x, then the globally defined operator has this degree of approximation. This is near the point x. Likewise, in order to get such an estimate, if you are interested in a fixed value of x, you don't need to construct this entire operator. You can only use the values of this function in this small neighborhood of x. Although this time this delta d fx will depend upon the radius of analyticity of this function. It does not depend upon n anymore.
Little n is what?
Little n is the degree of the polynomial.
Degree of polynomial, okay. And okay, so basically you're saying that we have an exponential convergence, right?
For analytic functions, you have exponential convergence.
For analytical function, yeah.
The function is analytic in a neighborhood of x.
Both globally and locally. The second one is the local, right?
Both of them are local estimates.
Or both local.
So I'm only assuming that the function is locally analytic at x.
Sure, sure.
If it is smooth on some other part, in the previous theorem will tell you that in the neighborhood of that thing, the same operator will have the degree of approximation, which will be according to the smoothness there. But we don't have to split the region beforehand to figure out what is what. This global operator automatically adjusts itself. Okay, this is about distributive learning, that you can only look at the samples in this small neighborhood of x. Okay. I should remind everybody again that this x is the value of the information operator applied to my input function. Okay, the bottleneck is the quadrature formula. So I wanted to figure out what to do if there are random samples. Lulu visited me a long time ago and he pointed out to me that in their experiments, they like to use random samples of the input. So here is the random sample version of it. I want to draw samples from a probability distribution like this. So if I'm interested in one target function, then it makes sense to use this f sub 0 to be supported on a small neighborhood of that point at which I'm interested in. So this covers both the global result as well as local sampling. And then I form this Monte Carlo average. Of course, it will not do as good as having an exact quadrature formula. This is the monstrous expression I got. So if you have so many samples, then with probability greater than 1 minus epsilon, this is we recuperate the right rate. But of course, this time it is going to approximate f0 times f, not f. So if you are interested in a local neighborhood of x, then you choose this f sub 0 to be supported in that neighborhood, and then you get a local approximation. If this f0 is 1, then you have a global approximation. And you don't have to know what this F0 is to construct this operator. It is just done with F. The F0 is implicit in the selection of these Y sub j's.
Which term is the quadrature error, Hrushikesh? Here. What term would tell me the quadrature error?
Here there is no quadrature error. Here is just a Monte Carlo sum.
Okay.
And this comes out of Hugh-Dim's inequality. Okay, then to put everything back together, here is an example. Again, there is a long setup here. I'm sorry, but I have to think of such a system where I'm dealing with operators defined on a arbitrary smooth compact manifold of dimension q. The lambda sub k and phi sub k are related to the Laplace-Beltrami operator in this way. The Laplace-Beltrami operator is a negative definite operator, so it has lambda k square as the eigenvalues. Phi sub k are the corresponding eigenfunctions. Rho is the distance, mu star is the volume measure. Pi sub n is what we call diffusion polynomials. I was introduced to this idea by Mauro Maggioni way back in 2005. I'm used to thinking in terms of orthogonal polynomials, and he was thinking in terms of heat diffusion. So we coined the term diffusion polynomial for this object. This is the degree of approximation from this space. And in this work, I will just talk about the Sobolev class for simplicity. If you have analytic functions in the sense of this converging exponentially fast, then the theory will be about the same thing. It doesn't add anything new. Okay, so I will focus on this class. And then I need, in this very abstract context, a strong product assumption that if you have a polynomial of degree n, polynomial meaning this, then the square will also be another polynomial of a slightly higher degree. Normally, this A star is just 2, but it's a strange situation. I cannot prove that this assumption holds for all manifolds, and I cannot display a counterexample either. And there are some theorems due to Pesenson and Geller where they prove that there exists such a constant if you have a homogeneous manifold. And we have extended it somewhat nominally. So that I don't know exactly when the strong product assumption holds, but I cannot prove that I cannot display a counterexample and I cannot prove it either. Anyway, so again, there is an MZ quadrature measure. This time I can afford to take this more common viewpoint where I talk about the L1 norm instead of the L2 norm. We have proved that in this context, they are all equivalent, but then the constants involved in the equivalence will depend upon the dimension of the manifold. That's why in the previous definition, I had to have a p square, so I don't get into that thorny issue. Okay, so once more, there is this analog of the theorem with Narkovich and Ward on the sphere. If you have a sufficiently dense data set in this sense, then there exists a Marcinkiewicz quadrature formula supported on this data set. You don't have to prescribe this data set. This can be randomly chosen or arbitrarily chosen, I should say. It's not like these have to be zeros of, it has to be like something like a Driscoll-Healy formula or something like that. It can be just based on any set whatsoever. So this is an existence theorem. There are theoretical algorithms to do this, but I need somebody to explore this numerically for me. Okay, so also there are kernels and operators on the systems. This time the kernel is defined in terms of a mask in this way. It's very important that this mask should be not only smooth, but it should be one in a neighborhood of the origin. And then these are the discrete Fourier coefficients. This is the discrete sigma operator, summability operator. And this is the analog of the theorem on the sphere, which you have seen before, except that now the constant will depend upon the dimension. Okay, so now because I want to approximate operators, I will look at two such systems. and every time I will indicate which system I'm referring to by the number there. So my frac X is the space of continuous functions here. The other matrix space is the space of continuous functions on the other space. The Kx and Ky are the unit balls of the Sobolev classes. In this case, I have to extend this F from this Sobolev class to the entire, to the whole Sobolev class, not just the unit ball. And I will explain on the next slide why. The script F is not a linear operator, but still I can use the fact that you can bring any function in the Sobolev class to the this compact set by just dividing by the norm of that Sobolev class. And then I have to compensate by multiplying this F by this constant. So if this input function F is in this compact set, then you recover the old value. If not, then this is the way to extend it for the whole Sobolev class. And then I will assume that there are such sets which are admitting mz quadratures of order an star times nj for some nj. Then it turns out that the magnitude of the cardinality of this C sub j should be like this as expected, and likewise for the cardinality of C2. And please remember this D and M from my previous slides. The D was the dimension of the information operator of this F, and M was the dimension of the information operator on this image space. So now the information operator is simple. I just evaluate this F at the points of C1. The algorithm back is expressed in this way. In the previous slides, I had written it as integral on the whole manifold, but for the emphasis, I'm writing this as the integral over C1. So this object belongs to a Euclidean space of dimension equal to the cardinality of C1. And the same with the image space also. And then we have proved in a paper together with Mauro and also some other papers with Frank, I don't remember exactly where. But the worst case error using this information and algorithms is given like this. And they are both optimal in the sense of widths. I don't remember exactly where, in which paper of mine I have done this, but it is known. So the reason for this extension was this technical problem. So after this information is collected and all, we need to go to the sphere to do the spherical approximation. And that needs me to evaluate the quadrature formula at certain points on the sphere. So the question is every point on this upper hemisphere the image of some function in my Sobolev class? And the answer is yes. If I think of eta to be the minimal separation of points in this set C1 at which my input function is sampled, then for n greater than the reciprocal of this eta, there exists such a function. This is a diffusion polynomial of degree n. Definitely it belongs to all the smoothness classes one can imagine. So if I take this as my f, then the information operator, when I project to the sphere, will have this value. So every point on this, with my extended operator, every point on this hemisphere arises at as a point, as an image of this kind of function. Again, this is not completely unknown, but it's a recent proof is found in this paper, which just got accepted for neural networks. Okay, so here is the summary of the whole thing. First, we have to find a finitely supported quadrature measure on the sphere of dimension d. And let's say that we are somehow able to find this, the W sub k is the measure, the value of weight associated with the point Wk. Then I have to find the function f sub k in the Sobolev class so that the points y sub k are obtained in this way. And then I have to compute my operator at these points and evaluate it at points in C2. All these are pre-computations. I have not seen the input function at which I want to compute the operator yet. This is a all this is a complete pre-computation. I imagine that it takes a long time to do this, and it is probably worthwhile if you are interested in approximating the operator at lots of different input functions. Okay, but then the algorithm itself is very simple. After all this pre-computation, all you have to do is evaluate the value of the input function at this point C1, project it to the sphere, that's the point X, and then use the kernel which I had defined. This is the output of this operator. And then this thing is approximating the information operator on script F evaluated at the input F. And then we just put it back together using the reconstruction algorithm. That's all. So here are some conclusions. First of all, I have looked at error estimates in the supremum norm. The custom here is to look at them at L2 norm, but I think the supremum norm is more relevant because we are interested in values of the function. In fact, the probabilistic estimates which I gave are perhaps the most are the best way of doing things. Then each box in this main processing step is a prefabricated network. You don't have to train that network. It's all already done in the pre-computation step. So the total number of parameters is not d times n times m, but it's just d plus n times m. I think that's a big reduction potentially. The bottleneck of this whole thing is the three quadrature formulas, two on the two domain and image spaces, and the big thing is on the sphere. If your data is dense, then you don't have to compute the F sub k's, but otherwise that also is necessary. All of these problems require solving large matrix equations. I think this is so far the bottleneck of the theory. I have some ideas on how to do this, but I'm not very good in programming, so I need some, I hope somebody will help me navigate this part. Apart from this, there is no training is required. You don't need any stochastic gradient descent, anything like that. Everything is done deterministically with estimates done in probabilistic sense. Then we are doing local approximation or distributed learning. So in small neighborhoods of F, we take the values to compute this value. We have a globally defined operator. Automatically it adjusts its degree of approximation. If this F is analytic, then it will give exponential rate in a neighborhood of that point. If it is just Lipschitz continuous, it will deteriorate accordingly, but not worse. Okay. Thank you.
Thank you, Professor Mhaskar. Questions for him?
I think Matthias has a question. Go ahead, Matthias. Unmute, please unmute your mic.
Thanks, George. So first, thanks for this nice, impressive talk. I have two small questions. So first, on your very last slide where you wrote the bottleneck, these matrices that you mentioned, are they sparse or full?
No, the matrices are effectively sparse, so one can formulate this in terms of the localized kernels, and then it's not entirely zero, but it is fast decreasing away from the diagonal.
Yeah, so it sounds manageable.
Oh yeah, it's probably well conditioned, but it's just that it's very large. So for example, if you are looking at a 10-dimensional sphere and degree 100, then it's a huge system.
Yeah, I mean, there are standard packages for doing integration with sparse matrices.
For sure.
But maybe they are not tuned to your case.
This I don't know. I have not written programs myself, so I'm hoping that with such lectures, somebody will be willing to help me with giving me a reality check about whether or not this is a hard problem or easy problem or how it is. Right now, I'm just looking at it and I'm just daunted by the large size of the matrix, but it is a well-conditioned matrix. It is effectively sparse also. So,
yeah. In fact, I think that the step to doing numerics is still a quite big step to do.
yeah.
Also due to these polynomials. I mean, you can use these polynomials, these Jacobi and Legendre polynomials in theory, but if you use this in numerics, then some of them are, how to say, they are not robust enough for calculations, and so maybe you will encounter new problems.
Up to 128, I think is okay. Up to 128, degree of 128, yeah.
I think that should be enough for most practical applications.
But the question here is, I mean, the question is, so basically what Hrushikesh is proposing is to replace the stochastic gradient descent with these computations of big matrices, which I think is a good proposition. One has to check the trade-off, because you will have better accuracy for sure in practice, right? Which you don't get with the solving an optimization problem for sure. And then these methods are more mature. Like you said, with 8 matrices, other ways you can actually tackle these problems. But I have a question, Hrushikesh, on the on the DPoNet, for example, we have a trunk, and the trunk produces this adaptive basis.
Yeah.
So you're saying that this adaptive basis is trying hard to mimic the Jacobi polynomials?
No, I'm saying that this trunk and such comes from an approximation of f of f in the to begin with. And it's all right when you are just interested in universal approximation theorem, just the density, but it doesn't give you any clue about the degree of approximation. In my paper, I have given an example where it's actually not the right way to do things. I have given a cooked up operator where it's better not to do it like that. Did I answer that question? So
I was wondering, because you sort of say, I'm going to work with this kernel, which is which you wrote nicely in. I have written a book full of Jacobi polynomials for spectral elements, so I like Jacobi polynomials. But you constructed your kernel based on Jacobi polynomials, and then you go on with that approximation. But so and the DPoNet doesn't have that. It has a trunk.
Yeah.
That gives you a basis. Sometimes we try to bias it with some features there, actually. But I thought that the trunk is my trunk is trying to, it's an adaptive basis, is trying to come close to your Jacobi polynomial, to this reproduction kernel, and get a basis like that.
That is possible. I think that step of the trunk and such is included partly here, where you select the information operator and then this post-processing step. Maybe this trunk operator corresponds to this post-processing somehow. But in my paradigm, I don't look into that. I have looked at it into a completely different way. So
right.
In my mind, when I looked at this tension expression with the trunk, then I thought here is a operator, and now he's trying to approximate the value of script f at f in terms of some Fourier basis. And then he's truncating it to get the trunk functions. That's how he did it in the paper anyway. But this is not necessarily the best way to do this. It introduces an additional approximation. This way of looking at it avoids the whole thing. It keeps track of everything at once. In my paper, there is an example where I have some information operator, and this post-processing is not done best with this trunk and branch approach.
Okay, I will look into it, yeah. And can you say something about d to the 1/6 what's special about the 1/6? I mean, it's better than 1/2, but what's special of 1/6? Where does the 6 come from?
Well, there is a bound on the Jacobi polynomials, so that if you are inside the interval from -1 to 1, then the Jacobi polynomials are bounded by some expression in terms of x, and there is a constant in front. And what that constant was a big problem, I guess, for people who worked in Jacobi polynomials themselves. And somebody proved in 2007 that the right constant there is the parameter alpha to the power 1/6. That's where the 1/6 comes from.
Okay.
I don't know whether it is the best possible or not, but that's the best I could find. I was just happy to get something tractable.
Yeah.
Do we have more questions for the speaker?
Is it not way past lunchtime for you?
It's okay. Not in Germany where Matthias is.
No, it's
Dinner time.
It's 7th evening.
All right. It was nice talking, and thank you very much for inviting
Yeah, thank you very much, Hrushikesh. Thanks for taking the time. I'll read the paper. Thanks.
Bye-bye.
With that, we come to an end to our seminar today. Have a great weekend ahead and have a great rest of the day. Thank you.
Yeah, bye. Thanks, Robert.
Thank you too. Bye.